Okay.
So we are now going to listen to the last presentation of this session by Professor Jinzenji, and the title is Elliptic Virtual Structure, Constants and Generalizations of BCOV-Zinger Formula to Projective Fano Hypersurfaces. So please start.
Thank you for introduction, and I would like to thank the organizers for giving me an opportunity to talk this topic in this conference. And the title is Elliptic Virtual Structure Constants and the Generalizations of BCOV-Zinger Formulas to Projective Fano Hypersurfaces. And BCOV is the abbreviation of the four persons' name, Bershevsky, Chakotay, Oguri, and Buffer. These are major string theorists. And this is the topic of the Gromov-Witt invariant and mirror symmetry. And this work is a joint work with Ken Kuwata from National Institute of Technology, Kagawa College. So first, I roughly explained the assertion of classical mirror symmetry for Calabi-Yau manifold. And mirror symmetry is a symmetry between two worlds. One is the A model, which is the world of holomorphic curves in the Calabi-Yau manifold, or Gromov-Witt invariants, which counts the number of holomorphic curves in Calabi-Yau manifold. And this is the world of nonlinear theory, nonlinear. And the other is the B model. And this part is the deformation of the mirror Calabi-Yau manifold. And its information is given by solutions of Picard-Fuchs differential equation, or ZKZ system. And this world is a kind of linear world, and it is easy to solve. And on the other hand, A model is nonlinear world, and it is very hard to solve. So the mirror symmetry is the kind of a way of solving a nonlinear problem by using linear problem. So the assertion of classical mirror symmetry is that the solutions of Picard-Fuchs differential equations are translated into generating function of Gromov-Witt invariants of Calabi-Yau manifold by using a mirror transformation, which is a coordinate change of deformation variables. And so it is easy to solve Picard-Fuchs differential equation. So by using mirror transformation, this function is translated into the generating function of Gromov-Witt invariant. That's the assertion of the classical mirror symmetry. Then, but in this talk, we treat B model as a slightly different way. In the series of works, our previous works, we have established another geometrical object that plays the role of B model. That is another way of solving Picard-Fuchs equation, or geometrical way of solving the Picard-Fuchs equation, and which we call this objective, which we call the virtual structure constant. And let us take the example of the Calabi-Yau hypersurface in CPK-1. And in the case of this example, it is given as the following residue integral. So this is a B model analog of Gromov-Witt invariants, and it is given as this residue integral. To tell the truth, it is derived from some more geometrical intersection number of modular space of Kessel maps. But in this talk, we omit this geometrical derivation, and we start from this residue integral. And this residue integral is associated with the line graph with D edges and D+1 normal vertices. And this is a kind of a reflection of a linear structure of B model. And so let us explain the notation of this integral. And EKXY is the monomial in X and Y given by this formula. And the residue integral represents the operation of taking residue at Zi and Zi equal to Zi minus 1 plus Zi plus 1 over 2. If I goes from 1 to the minus 1, because this integrand has pole and at here, where this has a pole, Zi equal to Zi minus 1 plus Zi plus 1 over 2. And we also have the poles at ZQ equals, Zi equals 0, coming from this factor. It is cannot be seen, but there is a pole at Zi equals 0. And we take these poles, we take residues of these poles. And if I equal to 0 and D, we only have pole at Z0 equal to 0 or ZD equals to 0. So we take poles at Zi equals 0, if I equals 0 or D. Then from this, we can obtain some rational numbers, which is a B-model analog of Gromf-Wheat invariance. Then we consider the foreign generating function of the Budget structure constants. So this kind. So deformation variable of B model is given by X, right? And this is the Budget structure constant. So this is some kind of a functioning X. Then Fart's theorem of us is that the 1 over k times this Budget structure generating function gives the mirror map used in translating B model into A model. So this is the coordinate change of mirror transformation, right? And then by substituting the inversion of xn equal to xt, i.e. t equal to tx, inversion of this mirror map, the generating function, the W generating function turns into a generating function of Gromf-Wheat invariance, which counts the rational curves in Calabi-Yau manifold. Yeah, right? So this is a non-trivial result. So this is the idea of the mirror symmetry. So, and I want to say that computation of this generative function is easy because we only have to calculate residue integrals, and it is very easy. But on the other hand, direct computation of the Gromf-Wheat invariant is very hard. So this is the merit of the classical mirror symmetry. So yes, and this is the example in the case of Calabi-Yau manifold. And we remark here that at early stage of study of classical mirror symmetry, mirror map and the generating function W are constructed from solutions of this Picard-Fuchs equation. So in this talk, we used residue integrals instead of this differential equation, right? Okay. So later, we generalized this result to be non-singular degree K hypersurface in CPN-1. So not only in the case of Calabi-Yau manifold, we generalized this picture to general hypersurface in CP-1. So including Fano hypersurface and the general type hypersurface. And we generalized the result introduced so far to the case of genus 0 Gromf-Wheat invariance of M and K. So in this case, we slightly generalized the notion of Budget structure constants into multi-point Budget structure constant, which is defined by this kind of residue integral. So the reference between the difference from the previous slide is this factor. In the previous result, in the previous example, there's no double, we have no factor like this. But in this case, we include this factor. And here, WPXY is given by this simple polynomial. And this resting theory is also associated with the line graph with d edges and d+1 normal vertices. So it is also linear, some kind of linear characteristics. Then we introduce generating function, march point Borges structure constant. So in this case, we introduce the n-1 variable from x0 to xn-2. And each xi is associated with the insertion of the operator OHI, where H is the hyperplane class of CPn-1 or hypersurface. Okay, so in this case, we consider march point Borges structure constant. So number of the deformation variable increases from x to x0 to xn-2. Then we also define mirror map, which translates B model into A model. And this definition is almost the same like the Calabi-Yau case. No, because in the case, Calabi-Yau case, mirror map is given by this generative function. But in the general case, we omitted the variables, but this mirror map is almost the same form, takes almost the same form as in the Calabi-Yau case. So this has the following structure. So this from this formula, we can see that if EX1 goes to 0 or x1 goes to -infinity, TP equals to XP. In this limit, TP equals to X to P. So this structure enables us to invert the mirror map by using perturbation, power series solution, power series analysis in EX1. Then we can invert the mirror map order by order of EX1. Then in this case, we can generate the classical mirror symmetry conjecture to this case. So by substituting the inversion of the mirror map into this generating function, this function becomes the generating function of Gromov-Witten invariance of M and K. So in this case, Gromov-Witten invariance has many varieties, but this counts the number of rational curves in M and K, satisfying some kind of passing through condition obtained from these operator insertions. So we can solve the curve counting problem by using linear kind characteristic residue integrals. And this conjecture is confirmed numerically by various N and Ks. And main topic of this talk is generalization of the conjecture to genus 1 Gromov-Witten invariants. In other words, counting genus 1 curve, elliptic curves in the hypersurfaces. So let us introduce setup of mirror computation of genus 1 Gromov-Witten invariants of projective hypersurfaces. So first, we prepare elliptic Borges structure constants, this kind. But this is related to genus 1 curves in the hypersurfaces, and which will be defined, and this definition will be shown later slide. Then up to now, we introduce some characteristics of this elliptic vertical structure constant. And first is the value of the elliptic vertical structure constants that corresponds to degree zero maps from genus 1 curve to hypersurface. And this is given by this formula. And the second is the selection rule of the elliptic multiple vertical structure constants, and given by this. And the third is the punctual condition or punctual axiom or Taylor axiom of the elliptic vertical constants. We omit here for details. But we have to note that these three characteristics are also satisfied by genus 1 Gromov-Whipton invariant, which counts the number of elliptic curves in the hypersurfaces. So the W invariant and the Gromov-Whipton invariant are rather similar, but in general, these two numbers are different from each other. And we want to say that W vertical structure constant is much easier to compute. Then we introduce generative function of elliptic vertical structure constants and that of genus 1 Gromov-Whipton invariants, respectively, here. And we call the B model generating function, which is a generating function of the elliptic vertical structure constants, and A model generating function, which is the generating function of the Gromov-Whipton invariants, right? Then our main conjecture in this talk is that the B model generating function, A model generating function is obtained from substituting X0 inversion of the mirror map, which was used in conjecture 3. Then B model generating function turns into translated into A model generating function. So this conjecture gives a recipe of mirror computation of genus 1 Gromov-Whipton invariants of projective hypersurfaces if we regard information of the elliptic vertical structure constants as B model. Then in the following slides, we present part of it definition of the elliptic vertical structure constant, which is a generalization of the definition of the multi-point vertical structure constants given by this formula. So we generalize this formula to genus 1 case. Then elliptic vertical structure constants are computed from adding up contributions from Feynman graphs. So we first introduced the graphs used in computing elliptic vertical structure constants. Then we prepare the following three types of vertices. First is the normal vertex, which is used in the previous example. And then second is the elliptic vertex. This represents some kind of infinitesimally small elliptic curve. And then we also introduced cluster vertex of degree D, which is represented by black circle over in the upper way. In the upper position, we write the letter D. So normal vertex and the elliptic vertex and the cluster vertex of degree D are assigned with degree 0 and degree 0 and degree D, 0, 0, D. Then An edge is represented by straight line and assigned with degree 1. Then we also introduced the partition of positive integer d. Let PD be the set of partitions of positive integer d. Then this is the generalization from the line graph. This is a generalization. So then we prepare the following 4 types of graphs of degree d. First is the star graph associated with sigma, partition sigma, and having a elliptic vertex as its center. Oh, this is a mistake. And then second is the one loop graph with d edges and d normal vertices. And the type 3 is the star graph associated with sigma of the, which is the partition of d minus f, and having cluster vertex of degree f as its center. Then type 4 is the graph which consists of a single cluster vertex of degree d. So let us show the figures of examples of these graphs. So first, type 1 graph. Example of type 1 graph is given by this. And this is associated with the partition 3, 3, 2, 1, 3, 3, 2, 1, and elliptic vertex as its center, having elliptic vertex as its center. So this kind of, this star graph has tails, 4 tails. So we need partition of integers to represent information of these tails. And the type 2 graph is given by this loop graph, circle graph. So we can easily see that the type 2 graph, we have only one type 2 graph for each degree d, for each degree. So degree 5, we have only one loop graph, type 2 graph. And the type 3 is associated with partition 3, 2, 1. So this is degree 8, but cluster vertex has degree 2. So we only have 6 edges. So there we have a partition of 6, and this tail has 3, 2, 1. Okay. So this is the type 3 vertex, type 3 graph. And the type 4 graph is consists of single cluster vertex. So we can also easily see that we have only one type 4 graph for each degree d. Okay. So let us write down all the graphs from type 1 to 4 for degree 1 and 2 and 3, right? So degree 1, we have only 2 types of graphs. So we have to note that the type 2 graph exists if only if d is more than 2, right? So in this case, d equal 1 case, we have 2 graphs, and d equal 2 case, we have 5 graphs. So this 2 graph is equals the number of the partition of 2 and 1 plus 1. And in the d equals to 3 case, we have 1, 2, 3, 4, 5, 6, 7, right? Okay. So we can see that the loop graph, each we have only one graph, one type 2 graph, one loop graph for each degree. So by using this kind of discussion, number of graphs for fixed degree is given by this, where Pj, this is the number of partitions of d, positive integer j. Yeah. So then generating function of nd is given by this formula, which is the easy combinatorics. So we can see, the degree 3 is 8. So there are some hiding graphs, right? 1, 2, 3, 3, 4, 5, 6, 7, 8, right? So from this power series, we can see that the number of graphs increases rather slowly as degree rises. Then let graph D be the set of all graphs of degree D, and graph D1 to graph D4 be set of all graphs of type 1 to 4 with degree D respectively. Then for each graph, each type of graph, we define integrand of the residue integral. So this is the generalization of the integral of the genus zero case, which was given by here. So the integrand gets complicated, but not so complicated, right? So for type 1 graph, we have a similar expression, right? Genus zero case. But the newcomer is the CTZ0, which corresponds to top chunkless of the hypersurfaces. Okay, and 1/24 is the characteristic number of the modular space of genus 1 curves, modular space of genus 1 curves, complex structure of genus 1 curves. And for type 2 graph, this is just a root graph. The integral is rather simple. And cluster vertex, in this case, integrand is most complicated in this setting. And type 4 is type graph, integrand is very simple. Then and newcomer CTZ is a monomer in Z that satisfies CTH is equals to Cn-2 top chunkless of the hypersurface. And symmetric factor sigma appears. Symmetry factors of sigma appears. And symmetry factor of sigma is given by here. And this corresponds to circle permutation of the elements of sigma. Circle permutation. Some kind of number of circle permutation of number of elements of sigma. And lastly, we also introduced factor RNKD. And this factor is very mysterious. And we don't know how we obtain this mysterious factor, but it is determined from numerical experiments. And it is very mysterious, but it is very powerful in our computation. So then we take the residue of these integrands. So these integrands have residues at this coming from this factor and this factor. So this is the explanation, but it is very complicated. So we explain from graphs. So each variable is associated with the vertex of the graphs. So Z0 corresponds to this and this kind of. So we associate the variables to each vertex, and we integrate from inside to outside, right? And in the type 2 graph, we integrate the variables associated with each vertex in the circle-wise, and we take residues. And in the cluster vertex, we also have to introduce ghost vertex W, which is also associated with the cluster vertex. And we first integrate W. So because for the type 3 graph, we W equals, we have poles at W equals to Z0. So we integrate first W, then from inside to outside. We take the integrate from inside to outside. And in the type 4 case, we have only one variable z0, and this is very simple. So this is integration is very straightforward. Then we denote by map res, which is the operation of taking residues of integrand f gamma. Then elliptic Barger structure constant is defined as summation of the residues of each integral of each f gamma, where gamma is associated with graph D. Gamma is the element of graph D. Then we can compute elliptic Barger structure constant as we like. So maybe people wonder how we found this kind of integrants. And to tell the truth, it is found from numerical experiments and analogy with the case of the rational calculus, genus zero case. So this is conjecture. So the results, which will be shown in the next following slides, our results are all conjectures, but we have tested these conjectures numerically by computer calculation. So let us first the example M41, which is nothing but CP2. Then B model genetic function is given by this. This is some kind of evidence. So evidence. Then mirror map is given by this. So each coefficient is obtained from this definition, and this definition, right? So of course we use computers and mathematical processing software like Maple or Mathematica. So these are the mirror map, and the inversion is given by here. Then by using conjecture form, we obtain generating function of the Gromfit invariance, which counts genus 1 curves in CP2, which satisfies some kind of passing through condition coming from operator insertion. Then from this result, we obtain a number of elliptic curves in CP2. So this says degree 1 elliptic curve is 0, degree 2 elliptic curve is 0, and degree 3 elliptic curves passing through 9 points in CP2 is 1. And degree 4 elliptic curve passing through 12 points in CP2 is given by, which is hidden. And number of degree 5 elliptic curve passing through 15 points in CP2 is given by here. And these results coincide with the results obtained from Getz-Raz equation or Virasoro conjecture, which was all the results in 90s. So in Getz-Raz equation and Virasoro conjecture, they don't use mirror symmetry. But in our case, we have succeeded by applying mirror symmetry to this kind of formula to obtain this kind of results. Then let us go to the Calabial case. And the Calabial case, we introduce some kind of notation, the genetic function L tilde MKK, which is given by derivative of W generating function by X. And we know that this function is very closely related to solution of the Picard-Fuchs equation, solution of Picard-Fuchs equation given by this equal, where? Oh, here, this equation, solution of this equation. So,
I'm sorry, just 5 minutes, 5 minutes.
okay. So, L2, this is the power series solution of the differential equation. And this is L tilde 1 is the derivative of mirror map by x. Then let us define the following function in x. This is the BCOV-Zinger formula, which was found by Barshadsky, Chekotiogury, Buffer, and Zinger. And this is the combination of the L tilde function and this function log and this simple term, top term. Then Zinger proved that the A model ground-fit invariance of the Calabi-Yau generating function of ground-fit invariance is given by mirror transformation of this kind of function. So this is the result, famous result of the classical mirror symmetry of the genus 1 level. Then, on the other hand, let us define the generating function of elliptic virtual structure constants given by here. And this W star is obtained from this definition, right? So then our conjecture is that this function equals to generating function of elliptic virtual structure constants. So then we apply this definition, the definition of W star right here. So note that the type 1 graph we have only one type 1 graph, and we have only one point graph for each degree. The definition is written as follows. Then we found that the type 3 graph, contribution of type 3 graph vanishes. So this is 0. This is 0. We found it, and we can prove, Kuwata proved this vanishing theorem. And then for this factor, for this type 1 factor, type 1 contribution, I combinatorily proved that this type 1 contribution is given by this, which is exact result. I have proved recently. Then false contribution is given by this formula. It is very easy to compute. So combining these results, we finally obtain another representation of a BCOV-Zinger formula given by this. So remaining non-trivial contribution is this, coming from one loop graph. So in other words, we have this kind of conjectures, which is very non-trivial. And numerically, we have confirmed for lower k. So actually, we confirmed the results from k to k. From k, we confirmed from k 3 to 10. Then, in the case of the quintic hypersurface case, the left-hand side becomes this, and the right-hand side becomes this. Oh, so you can see that these two results are exactly the same up to degree 5. Okay, that's all. Thank you. This is the end of this talk.